And I'll start now.
Yeah.
So, good evening, everyone. On behalf of ISI Bangalore student, I welcome all participants to the next talk of the Limit Mathematics Online Camp. I have great pleasure in welcoming Professor Rajat Hazra. He obtained his PhD from Indian Statistical Institute, Kolkata. Following his PhD, he held postdoctoral position at the University of Zurich. He was a faculty member at ISI Kolkata before joining Leiden University, where he is currently an associate professor. He was awarded the prestigious Shanti Sarup Bhatnagar Award for the Mathematical Sciences category in 2020. His research interests mainly probability and more specifically extreme value theory, heavy-tail processes, random graphs, and random matrices. With great honor, I welcome Professor Hazra to deliver his talk today. Over to you, sir.
Thank you, Bikram, and thank you to the organizers of the Limit Camp for inviting me. It's after a long time I'm giving online talk, so it's almost after COVID period. I have forgotten a bit about online talks. So, and I want to keep the talk a bit light. So what I want you to do is, if you have any questions, then since it's a Google Meet, I don't see if anyone is trying to communicate with me. So if you're writing in the chat, then I will ask Bikram to stop me anywhere and ask the question, or you can unmute yourself and also ask a question. So feel free about that.
Sure.
And I hope, I really hope that your camp is going well. You have a fantastic lineup of talks. So I want to talk about today somewhat, it started as a curiosity, and now it's emerging as quite an interesting thing. So it started as like many of you are now in school. So I was asked for some school students, in fact, to think of a problem about 3 years back. So this was in Netherlands, and yeah, and then I had to think of something which is kind of interesting but easy, but and can be also tackled with some basic knowledge. And then I stumbled across this friendship paradox, and I'll tell you what this paradox is all about. And uh, but before that, what I want to start, so I also want to talk about social networks. Now, social networks is a fancy name. Uh, as you can, uh, we all know what our social networks are in today's days. So the first question is, what is a social network? Now, social network, as we all know, are like online apps or something where we communicate with other people whom who may be physically our friends, who may not be physically our friends, who may be peers, who may be anything else. But for mathematician, what is a sort of a social network? We are not exactly sociologists and everything. They will also play a role. I'll come to it later. But what is a social network for me? It's so let's take an easy example, which I think most of you are sort of aware of this. So this is taken from Reddit actually. So this is a Harry Potter network. So it's created out of the characters from Philosopher's Stone, the first book. And for me, so for a mathematician, when one looks at this structure, so for me, you see it's a bunch of dots and lines. The dots represent the characters in the story, and lines can represent many things. For example, in this graph, the lines, as you see, there are multiple lines which represent any kind of interaction. Now, this was done in Reddit by some people. So what happens is, so there is a beautiful software called Gephi, Gephi, Gephi. Gephi is a very nice software. So what you can do is you can put in the vertices and edges, and it plots you this kind of beautiful graph. Now, this graph is not completely correct in a way if you know the stories. For example, I don't know if this is visible. So there is a place where there is Vernon Dursley, and I think there is Lily Potter, and there seems to be a link between them, which cannot happen. So I'm not very sure that this graph is correct, but it kind of gives you an idea what a network looks like. Now, what you can ask, so as a mathematician, you can ask, okay, what is this actually plotting? Okay, it's plotting these things. Why does Harry Potter look so big? Now, Harry Potter looks big. The reason is that the book is about Harry Potter, so it's about whom he meets and everything. So he has a lot of connections there. And so the line signifies, I think I got a question which popped up. So the line signify whether there has been an interaction between the two people involved in the whole graph. Like whole story, if Harry Potter say talks to someone or some interaction is happening, then there is a line. Say Harry Potter talks to Snape, then there is an immediately line between Snape and Harry Potter. And so this is the interaction graph. So even you see, yes, so what I was saying, the size of the circles signify the number of edges or the lines which are going out from the vertices. So the higher number of connections or a higher number of lines, the blobs are a bit bigger. And so this is a way of plotting this. This is yeah. So what was the question? I can't read the full one. Somebody asked another question.
Yeah. So essentially, the strength of relationship between two characters is the number of lines, and the number of connections shows the character's importance.
Yes, but it's not only between two characters. For example, why is Harry Potter more? Is because Harry Potter has connections with the Dursleys. Harry Potter has connection with Hagrid. Everyone in this whole story, everyone is connected to Harry Potter. So he has more friends. So if you think of these lines as friends or enemies or acquaintances, so Harry Potter has more acquaintances. So that's why the blob is a bit bigger. So he is, if you think he's the superstar in this. Then there is Ron Weasley. Ron Weasley is equally famous because of his father. So, and Percy Weasley is also there. So, and Hermione Granger is, okay, the story kind of interacts a lot with Hermione Granger. So that's why this is there. Now, okay, I'll come to this graph. I'll come to this graph in a moment. But social network, as I was saying, is mostly about nodes and the lines between them, which we call edges. Now, what is a broad mathematical? So network modeling has not been paying attention. So mathematicians didn't pay much attention to network modeling. But in modern days, what is happening is there are immense amount of mathematical challenges which come in network modeling. So what is a network modeling? Is a question which, okay, sorry, is a question that how do you describe this graph? It's a bunch of dots and lines. What do you describe about this graph? So that's what I'll try to explain you in this hour quickly. But the idea is that you want to give some properties to these graphs so that it aligns well with the real world. So you don't want to go away completely from the real world. So real world means real world networks, social networks, Facebook, Twitter, Instagram, LinkedIn, financial networks. So this is financial networks are the first ones to be modeled mathematically because it involves money. And so there is relation between interbanking. So interbanking maybe is like SBI is working with different branches. So that's an interbanking. Intrabanking is like SBI, HDFC, ICICI. So they are interacting. So this is one kind of network. And then there are loan schemes which people give. People and bank have these networks. Then there is another important, which played a crucial role even in the recent COVID, was biological network. The first biological network which people decided was protein networks. So it's a protein-protein interactions, how they behave. Then the most complex network in the whole universe is the brain network, which very few people understand how it works, how it even operates. Even so today, if you are aware of AI, they are working on neural networks, which are kind of trying to model a brain. But brain is extremely difficult to model, because brain is one of the most complicated objects in the world, in the universe, in fact. So collaboration network, which is like, if I write a paper with say Bikram, then we are collaborators, so that forms an edge between us. And movie actor, so I'll show you a graph for the movie actors. So if two people act on the same movie, they are again connected. So this was a glimpse of what is one of the graphs, which is quite famously studied, is the Brazil interbank network. So it's so as you see, it's again a bunch of dots and lines, which look very similar, by the way. If you just glance, this is just some abstract art which was created out of the Harry Potter network, but it looks kind of very similar, although they kept the same size of the dots, but you can change the size of the dots also. And so they look exactly similar. These are more caricatures, but if you go to Geoffrey, they also plot this. So these are social networks which are kind of available in, you can get, one is from the Twitter, one is from the Facebook. Now Twitter, so you have to be careful, every network has its own property. For example, Twitter is a directed network. For example, you follow someone, but that person need not follow you. So essentially, so Facebook is when you accept a friend, you become mutual friends. So your friend counts immediately increase on both sides. But if you are on a Twitter, you generally follow a person. The person you are following, say you are following a cricketer, Virat Kohli, then you follow that person increases its follower, but you don't increase your follower because you have to do it yourself. So it's a directed network, and this kind of direction is kind of very common feature in many of the networks in these days. So I'll speak how to model them also. And this is, as I was saying, a famous, all from the net. I didn't prepare it. So this is a network of Hollywood actors. And you can see that Tom Hanks is quite big there. DiCaprio is big. There would be more actors who. So what this graph means is that, so what are the connections with, okay, again, these are generated by all these software. Sometimes they are wrong. I don't know of a movie where Johnny Depp and DiCaprio acted together. Maybe they have. I don't know if you remember anything, but they still show. It means that if two actors have acted in the same movie, there is a connection between them. So definitely Tom Hanks and DiCaprio has acted in a movie, so they have a connection between them. Now, again, if you look at the structures, now they have put in a big blobs, in the sense that whichever person, say DiCaprio, has acted in movies which had multiple big casts. So if a person has acted in a movie which has big cast, so it has more connections. So that's how the connections are built here. So my idea of showing you these pictures was, just by seeing these pictures, immediately you don't guess what is there. So what do you have to do? Now, network modeling comes, so what you want to do is, you want to throw in a bunch of points, and you want to have certain connection probabilities. So here is somehow what we ask ourselves. So in the first picture, I think you can see my arrow. So these are just bunch of dots in R2. So in the two-dimensional plane, say in a box. Now you ask, so how do I connect these two? Now I have shown three pictures here. So as you see in the picture below this, what happens is the PXYs I am choosing are quite small. So they have low probability. So what does pxy signify? Pxy signify that the probability that x and y are connected. And if the probability is low, that means your graph has very few edges in them. So I increase a bit, and then I see there are more edges, and then I again increase a bit, then I see quite a dense graph. So there are lots of edges between each other. Now the question is, how do you choose this pxy? Firstly, so that it kind of resembles something in real life. And the second is, if suppose there is a connection between x and y, what is the relation between, say, x prime and y prime? So how do you determine the role of x prime, y prime if xy is chosen? So these are some critical questions which we want to mathematically handle. Now let me, because I want to talk about graphs and networks, so I don't know if you're all aware of these languages, so I'll just repeat a few technical. So xy are just points on R2. Think of them as just points on R2 in the real line. So it's just you take 2 points. So you have a box, you throw in, say, n points there. So these are just randomly placed n points, and x and y are pair of points there. And you assign, then you decide whether there is a connection between them. There can be connection, there can be no connection, but what you do is you assign a probability that there is a connection between them. Now, what we want to know, as you saw in these graphs, what is important is degrees. And degrees, I also say, is the number of friends. In whatever I'm doing, I'll talk about degrees as number of friends. And what is this? For any point or any node, dx denotes the number of edges which have direct connection with x. So not proving direct connections, but they have direct connections. So dx is just the number of nodes that share a direct edge with x. Now, as you see in this picture, what is represented is there is this middle dot from where these red ones are coming out, big red shiny ones are coming out. This indicates that this point has a lot of edges. And this is a classic thing, that this is called a hub. So hub, we know that when we say something is a hub, means that it's a center point, and there are lots of connections. So you're in Bangalore, the bus stop near the station is a hub, because there are lots of buses which go from different directions in Bangalore. So that's a hub. So it has multiple places for which the buses go. So transport network is a kind of a valid graph network we'll be talking about. Now these hubs play a very important role. Yes, so there was a question, very good question. There can be multiple hubs. In fact, there will be multiple hubs in real life networks, because, for example, you can think of, say, Twitter. Twitter, there are so many people now who are, say, Elon Musk himself is a hub. Trump is a hub. Narendra Modi is a hub. Virat Kohli is a hub. So all these are big hubs, and they have a million people following them, or multiple billion people following them. So these are big hubs which are there. Now, one thing to note, because I'm a probabilist, I like to think about probability, since there is always, so when you are modeling, we don't know whether x and y are connected. So there is a probability that x and y are connected. So these connection probabilities are random. So this means that the dx variable, the degree variable, is also random in most of the cases. Now, we'll try to understand what this dx random variable is actually. So another notion which will be very, okay, I'll come up with different things, but this will be also interesting, is, so this curly cx is called the set of points which are connected to x. Now, connected here I mean path connected. So you start from x, you start traveling. So first you go to z, then you go to z prime, then you go to w. So W is a point which belongs to Cx. So essentially all the points which you can visit from X directly through edges. So this is called as Cx, and this is called the connected component, or it is also sometimes called the cluster size. So the cluster size is very important in our graph. So for example, this one, so I picked a point which is in the center. So in the graph, you see there is, the first one is just a graph. And then I try to point one point here and try to look at its connected component. I see almost the whole of the graph is in the connected component. Maybe there are few isolated points which are left around, but almost the whole graph is there. So what becomes important mathematically is that when you model, what is the size of the largest connected component? Now you can think why this is important. Because, say, for example, when in COVID, we were always talking about how much is the infection spreading. Or say, for example, nowadays, what happens is, all countries are crippled with fake news. Say suddenly there is a fake news. So what people try to do who are in the IT systems and cybersecurity is try to understand, say within 1 hour, what is the region in which this infection or the fake news will spread. And they try to kind of limit the information, because if they know the size, how much they will spread or the connected components they can reach, they can act on it. And that's why the size of this connected component becomes extremely important. Now, okay, so these are two notions. There are various other notions. I'll come to it. So the question, as I was saying, like, so these are some mathematical questions one should ask. So what are the connection probabilities Pxy one should choose? How to model a random graph which represents real life networks? This we talked about, but we haven't talked. I'll tell you what things to look for in real network in a moment. So how does a random graph look like? So I showed you some pictures there. Now, these are not very nice pictures. You see, what we learn in mathematics is every picture is very nice. We have a sphere, we have a donut, we have a torus, we have nice, we have a bottle, Klein bottle. So all are topologically very nice looking. You can draw pictures, you can cut them, you can do them, but graphs don't look very nice. So how does they look geometrically? So they are much more complicated discrete objects to look for. The next question is, what is the size of the largest cluster, which I told you, like why it is important. So I'll not talk about phase transitions and too much of the rumor spread or other things, but these are also very important mathematical questions one can ask in this. And these are all pretty new, in the sense that mathematicians only started getting interested after it became, like after 2000, let's say, like people really understood that there is great mathematics to be done in these areas. So just let me show you with the simulation what is the role of a hub. So, oops. Okay, so let me just pause the. So the first picture which is running on the top, you see, so what is this simulation doing? It's picking up a point at randomly and starting an infection there. So what does it mean? That if you, so it's picking first uniformly one point among the green dots. It's picking that point and then choosing uniformly one of its neighbor and then putting the infection there. And then it goes on for the same amount of time. And there is a rate at which the vertices can recover if they are infected. Now, what is happening is, so there is a dichotomy between the rate and the infection. Now, this infection in the first graph, as you see, stops pretty quickly, because then it doesn't get other, because there is a vaccination which is going on at parallel. So somehow they don't get chance to infect people, and the vaccination kind of dominates, and the infection kind of stops only at 19. The second one, okay, sorry. So the second one, the point I choose immediately is sort of in one step going to a hub. And once it goes to a hub, it spreads to multiple number of points. And as you can see, even if the vaccination rate is, I put it a bit low at 10, but immediately you see within fraction of a second, there are like 472 sites which have been infected. So if once the infection spreads to the hubs, now it immediately spreads. Okay, so these hubs are quite important, and it may seem that, okay, why are there hubs, and how to tackle that, and is there always an hub? Because when we join social networks, we see, say you join Twitter, you immediately get feedbacks on saying that, okay, there are multiple people with huge number of millions of followers. Now, sorry, yes. So this question is, can you repeat your question? So I saw a question. So does the hub have
Saying
a,
that can a hub have a capacity?
okay, I don't know what it means, because capacity in mathematics can mean different kind of things. Because so hubs can have different properties. Yeah, I don't know how to explain that immediately, but I can tell you how hubs are formed later in the, like a cap to connection it can have. See, there is no restriction because I haven't told you what the graph is about. So in general, there might be the huge. So when we'll go to some specific graphs, I'll tell you what it happens. So these are very graph dependent, what kind of graphs you're considering. Okay. So let me go to the second part of the title of this talk, which is called What is a Friendship Paradox? So Scott Feld is an American sociologist who is an active researcher still. So he published a paper which is called Why Your Friends Have More Friends Than You Do. Quite intriguing, but sociologists kind of likes to think about these things. And so I'll for the moment let you read what is written in the abstract of this paper in the first line. So it says, it is reasonable to suppose that individuals use the number of friends that their friends have as one basis for determining whether they themselves have an adequate number of friends or not. And if you sit down for a while, those who are in social networks, those who avoid, very good, like keep avoiding. Those who are in social networks, you enter a social network and immediately you see, there is a friend from my school days. He seems to have like 1,300 friends. Wow. So yeah, I should also try getting so many friends. So this is the first impression you get. Now this paper kind of proves that this is always true in any graph. And this is the fun part, that so whenever you are considering in a graph, so your graph, and friends here means those lines. What you see always, that at an average, so this word is missing because it's a sociology paper. So at an average, your friends have more friends than you do. Now, this is quite intriguing. Why is this true? So this was kind of my starting point on trying to understand what it is showing. And then I went into a bit of the recent papers on sociology of social networks and other things, although I'm not a sociology person, but there are something called a majority illusion. So in the sense that whenever you get into a system, you see that you have a friend who is gathering all the benefits, like, okay, he's popular, he's everything. Or on the other hand, like, so why is this happening? Now, this is a very intriguing question, that why does this happen, that you always see someone who is kind of popular among the networks. Now, what the social scientists say, that this is an illusion. You feel that the person has more, but it's not really true. And this, what we finally discovered, that this is indeed not really true, and this is indeed an illusion due to some very easy mathematics which you see. Now, if you think of paradox, okay, for me, when I saw this, okay, paradox for me, the only paradox I know myself is Banach-Tarski paradox. Now I thought, okay, mathematicians think of Banach-Tarski paradox. It's really a paradox. It's a set theoretic thing which has a lot of intricacies in it. Now, what does a sociologist mean about paradox is the one I am talking about, that this is already an illusion. So this is paradoxical in their term. So it's not mathematically paradox. So it's not, for example, avoiding any axioms of mathematics. So this friendship paradox is actually a friendship theorem, you can say. So it's just a name, it's a fancy name, so we go by it. So what do I mean mathematically about this statement? So the statement says, in the paper also, it says, on an average, your friends have more friends than you do. So let's try to make precise mathematically what does this statement mean. So di is the degree of a node I. So d sub I, so you take a point in your graph. So think of all graphs for me are now finite. Don't think of infinite graphs. So I have n points in my graph, and di is the node degree of the node I. So this is the number of friends I have. So I means I have. Now look at my friends. So I have, say, 20 friends, and I put this in the set Ni. Ni is my neighborhood or my direct friends. And then for each of my friend, I count how many friends they have. So for example, I count Bikram. So Bikram is my friend, and I count the number of friends Bikram has, and I put it as DJ. So D Bikram. And then I count some other person. So maybe Yogesh or Manju, and then count their friends and put them. So this is the total degree of I's friends. Now I do an average. So by average, I mean I divide by the number of friends I had, 1 by di, and then sum over this thing. So this is the average degree of I's friends. Then what do? I take that bias. So I take the difference between the number of, so this average degree I had and the number of friends I actually have. Okay, so I take this bias, and the claim is this 1 by n. So 1 by n is the total number of, n is the total number of points I have. And then if I sum this is always non-negative. So it means if you rewrite this difference, it means on an average, your friends have more friends than you do. So my bachelor or the school students kind of came up with a very nice nomenclature. He said, this looks very bad and sad that my friends have more friends than I have. So let me put it as my friends have more enemies than I have. Like, so just change the word friends to enemies, but the theorem remains true. So, but somehow he said that I feel satisfying that my friends have more enemies than I have. So, so this is another perspective to look at. Okay, so is this clear? Anybody has questions? Because these formulas, although they are formulas, they will play the crucial role in this later part of the talk. Okay. So if you are fine, so let me give you a subgraph example. So let's go back to the Harry Potter example, and let's see how this is calculated. Okay, again, the graph, I used ChatGPT last night to generate it, made a mess of the graph as usual. So okay, there is only one mistake. So essentially, Snape and Hagrid are not really friends. So in a way, in my graph. So okay, so let me say I have these characters. I have 9 characters total. So Harry, Ron, Hermione, Ginny, Neville, Luna, Dumbledore, Hagrid, Snape. Now I list down the number of friends they have. So 5, 4, 5, 4, 3, 2, 3, 3, 4, 3, 2. So these are the degrees they have. Now, what I do is I calculate, as I said, the sum over dj, j in the neighbors of I, and these are the numbers, and then I calculate the average. Okay, so somehow you can't see, right? Okay. Oops, I think I missed. Yeah, okay. Now somehow if I want to change something, no. Okay, now it's okay, it's visible. Now I wanted to show you the bias because that's kind of important. So I calculate the bias now, which I was saying, this friendship bias. Now you see Harry has a negative bias, minus 1.2, Ron has 0.25, Hermione has minus, then 0.25, then 1, 1, 0.25, minus 0.25, Hagrid has 1.67 and 2.5. Now this was very intriguing for me when I did an example here, like can anyone tell me why this looks very strange? Now, as you see, I calculated the friendship paradox, and the average bias is always non-negative. This I'll prove to you also. This will be true, 0.44. But this caused me some discomfort in the sense that Harry had a negative bias, although he has more friends than most of the people. And Snape, who has the least amount of friends, had a very high positive bias. Although if you think like, okay, why, so, okay, Snape is friends with Harry, but Harry also has a negative bias. So, but still, this was not saying much about the biasness of each of these individuals. What the friendship paradox is telling you is that this quantity, if I take the difference of between 4.11 and my 3.67, then this is always non-negative. So that's what the theorem is claiming. Now, so the friendship paradox is true in Harry's world. So let me try to give you a mathematical proof for this. So what I do is I start with n. So as I said, I'll start with n points, and Gn be a finite, undirected, connected graph. It need not be connected, but I'm still assuming it's connected for simplicity because I want to convey the idea here. And di denotes the degree of this vertex. And now what I do is I write the, you remember in the previous formula, I had the sum over j in my neighbors. So instead of writing this neighboring set, what I do is I encode this in a matrix. So my matrix is called the adjacency matrix. So it's an n cross n matrix whose ijth entry denotes the number of friends between I and j. Now undirected means that I and j and I are all same. So they don't, so it's a symmetric matrix. So aij just denotes the number of friends between I and j. Yes, this is graph theory. So this is also, yes, this is graph theory. Definitely this is graph theory. This is a graph theoretic proof. And yes, so I'm going over again. So I have these degrees. So if you recall the bias is, so think of, I have only, either I have a friend. So think of this situation, simple situation, that's easy to understand. So suppose aij is 0 if I and j are not friends, and it's 1 if I and j are friends. So this is a simple situation. Now, what is this first sum on the numerator doing? It's summing over all j, aij, dj. Now, if I and j are not friends, this is 0. And this is 1 if I and j are friends. So essentially, the sum on the numerator, you see, is only summing over friends of I. So who are my friends? So I'm just summing over the i's. And then I'm dividing by di, and that's the average of my friends. So average friends of my friends minus di, the number of friends. Yes, this is minus di. Now, okay, so this was, now as I said, the friendship paradox is claiming that 1 by n delta in is non-negative. And even it says that this is 0. Yes, we are defining this. We are not deriving this yet. So this is the definition of the bias. So delta in is my bias. So the bias is, as I said, this bias is the one which is calculated in the last column. So this is the definition of the last column, which I'm putting here. So for each individual I, so for example, I here, so delta in is my bias. Now what it is saying that if you sum over all the biases, then it will be at an average non-negative. And it will be 0 if the graph is regular. So it means regular means everybody has same number of friends. So a graph is regular, that by definition means that it has same number of friends. Is this clear? Okay. Okay, so let's go through this proof, although I think I had an animation, but okay. So sorry about it. I thought I had an animation for this formulas, but it has gone. Now, think of the easy case, as I was saying, that Aij is either 0 or 1. 0 if I and j are friends, 1 if 0 if I and j are not friends, 1 if I and j are friends. As I was saying, the graph is undirected. So if you sum over all j's, then what you get is my total number of friends, Aij's. So if you sum over Aij's, you get the total number of friends, which is exactly di. The first step in the first line, what I do is I replace the di by the sum over ij's, Aij's. And okay, so that's what I do. I replace, sorry, this cursor is not also showing up. So I replace the minus di with the summation of Aij's. And then I take the Aij's common out of this whole sum. So I have a sum over 1 by n, sum over I, sum over j, Aij's, dj, di minus 1. I put this constraint that di, dj is non-zero just to make things well defined. This is, you shouldn't bother about it because it's a connected graph. There is at least one friend everybody has. So this is for the formulas, this is redundant. Now the question is whether this quantity is non-negative or not. I play this trick. This is a very famous trick in mathematics. What you do is you write the same sum twice. But what you do is in the second sum, so I'm taking the sum in the first line and I'm writing it twice. But what I'm doing is I'm just, because I and j are just indices. So no, it's not like Chevy Shave. So it's called a symmetrization trick. So what I'm doing is I'm writing the first sum as 2 copies of the same thing. And that's why I'm adding a half there on both the terms. And what I'm doing for the second term is that if you see the roles of I and j has been swapped. Yes, exactly. The role of I and j has been swapped, but this is just indexing. So indexing shouldn't matter for you, but this symmetrization trick does miracles. So what you can do now is Aij's is same as AJI because I'm friend of you, you are friend of mine. So Aij's are same as AJI's. So you swap the sum and then you take it common. So what you get now is that with an extra factor half, 1 by 2n, sum over I, sum over j, Aij's, dj by di minus 1 plus di by dj minus 1. So this is, okay, dj by di plus di by dj minus 2, which is very nice because this is just a square. And Aij's are non-negative. So this whole sum is just a non-negative sum. And you precisely know when this will be 0. This will be 0 if di is equal to dj whenever I and j are connected. And this means that whenever I and j are connected, the whole graph is connected. So all the di's are same. So the graph has to be regular for this to be 0. So in regular graphs, you don't see friendship paradox. In regular means, so in a world where everybody has equality, you don't see somebody having a majority. So you don't see this. So this is one proof, by the way. You can try, there are multiple proofs of this. You can try yourself. In fact, this can be also proved through Cauchy-Schwarz inequalities. So this is as true in our world in mathematics as Cauchy-Schwarz inequality. So yeah, in the proof, I assume that everybody is connected to everybody. So if this is 0, then it's a regular graph. Otherwise, it's not a regular. So everybody connected to everybody means it's a regular graph. Is this clear? I didn't understand the question. Can you... Okay. Is there any problem with the proof? Anybody, any questions? Okay, good. So now what we are, okay, I'm almost, okay, I took a bit of more time, but it's fine. So what we wanted to ask was, this was, as I was saying, it was not capturing the true essence of what I wanted to look at, is all the individual bias of each people. Now, the way to look at this is not through the sum, as I was saying. It's, so what I want to look at is this red object, which I have defined, is I want to look at, say, x is a real number. I want to look at the proportion of bias that is less than x. And how do I count it? I put an, so this one, bold one, is an indicator function. It means if delta in is the bias, so my bias, if it is less than x, the bias of I is less than x, then put 1, otherwise put 0. So it's counting exactly the number of biases which are less than x. And then I take the fraction of that. So this is the proportion of bias less than x. Now the question we ask actually is, say, suppose my graph becomes very big. Where does this function have a profile? So fnx, does it converge to fx? If it does, it tells me that there is a profile function under which you can determine what is the distribution of the bias. So it will tell you about all the biases you have. Not only that, it's the average is bigger than 1, bigger than 0. So for example, in probability theory or in integrals, when you're doing, say if I tell you about a function, okay, I give you a function. I say the area under the curve of this function is non-negative. Okay, so what? Can you tell me about the function? No. Now this kind of derivation will tell you what the function is. Friendship paradox is exactly saying that. It's saying that the area under the curve is non-negative. But that's not enough. So we need more information about this. Now the question is, what kind of graphs get large? So let me go to this last part of this talk, and I might be skipping few slides. So what are random graphs? We just talked about graphs yet. So as I was saying, so there are 3 properties in real life network which become very important. One is what is called a scale-free nature. Another is called a small world phenomena, and another is clustering. So let me go quickly through these. So what is power law degrees? It means if I look at the number of connections I have, remember my degree is a random variable. So if I look at the probability that I have k friends, then it decays like k to the power minus some exponent. And in real world, it is shown that this exponent is between 2 and 3. So I have given you some examples. So this is what it is called, that the degree sequence is power law. So the number of friends I have is decaying as a inverse polynomial. Small world property, many of you have heard. So these are posters from play. So this came into thing is the 6 degrees of separation. So this is a movie also from Will Smith, which is a 6 degrees of separation. So For example, nowadays 6 degrees of separation has reduced to 3 degrees of separation due to Facebook. So it means that you pick uniformly 2 points from your graph. Okay, what is the least number of edges you need to connect them at an average? Now, previously it was conjectured through an experiment conducted by Milgram that it is 6. So, for example, here it says that what is the chance that the president of United States and Gondolia, they will be just separated by 6 people. So this is what is called the 6 degrees of separation. Now, for example, like Zuckerberg has 3.15 degrees of separation. So if you pick Zuckerberg and any other person in Facebook, then it takes exactly 3 people to reach him. So this is what is called a small world. And small world has now reduced to ultra small world also. So because of many things, I'll not go into this, but this is a feature. And another is, which is very crucial, is clustering. That if 2 people are connected, no, this need not be directed. So these are true for directed and undirected, both of them. So both the graphs. So clustering is a feature. Yes, Mark Zuckerberg is seen as a hub because it has low degrees of separation. So that's one way to see that, okay, it is a hub. Now, what happens is clustering is that connected particles tend to share common friends. So, for example, wherever there is a wedge, there has to be a triangle. So if A is friend with B, A is friend with C, then most likely that B and C are also friends. So every wedge in your graph becomes a triangle. And this is what is called clustering. And if you take the ratio of the number of triangles divided by the number of wedges, this becomes positive in your sense. Okay, so there are many other properties. Due to time, I'm running out of time. But these are 3 main properties which you aim while modeling your graph. Okay, now can we model them? So yes, there are models which we can model. So let me just talk about one, and then I can, if you need, you can mail me. I can share my slides. You can look into other models. So this is a mathematical model which was proposed by Erdos and Renyi. Paul Erdos, as you know, is a big mathematician. Renyi is no less. So for example, okay, this is Paul Erdos's collaboration graph. So he has collaborated with so many people that there is a collaboration graph for Erdos. So these are the number of people who have collaborated with Erdos and also between themselves in a way. So this is the collaboration graph. Renyi is famous for, just to give you an example, Renyi is also famous. In fact, one quote is always contributed to Erdos, but it was by Renyi. A mathematician is a device for turning coffee into theorems. So this is what we always hear, that, okay, mathematicians are drinking coffee and turning theorems, which we don't actually, but it just turns our stomach bad. But anyway. But it's a quote. Generally, it's by Renyi, but attributed to Erdos. So let me give you a quick view on what is an Erdos-Renyi random graph. So you choose endpoints, and now you fix a parameter p. What you do is you toss a coin, and which has probability of head with probability p and tail with probability 1 minus p. And then for each of the edges, I and j, you toss a coin. If it lands head, you put an edge. If it lands tail, you don't put an edge. And you do this independently for any ordered pairs. So here I have asked the computer to do that. So the computer is doing this. So you see, like, it's tossing a coin and then deciding whether, so you don't see the coin tosses when it's not putting, but when it's putting the edges, you see that it's putting edges between in this graph. So you clearly see that this is. Okay, so this is an Erdős-Srény random graph. I'll not go into, okay, so I'll have to skip multiple. Sorry about this, I have to skip. It's slow. So there is something called a configuration model. I don't have time. I'll just skip that. So let me add briefly what is happening with this model. So this is also called preferential attachment model. It's also called rich getting richer. In this network, it's like a bit like a Facebook network. So Facebook network keeps growing. So the Facebook network keeps growing, and so every time one person enters an existing graph. Now, what is happening in this graph is that one new person comes to the graph and sees the whole graph. The person comes and sees the whole graph, and the person connects to the person who has the highest number of friends. So you enter Twitter, you have opened the account. The first thing you do is, okay, I'll follow Virat Kohli, or I'll follow Sachin Tendulkar. So they have very many friends, so you connect to them. You don't connect to someone who is like, okay, one friends or two friends or three followers. You don't do that. And this is why this model is called rich getting richer. That every time a new vertex comes in, it tries to connect to an existing vertex. And this has an hub effect in your graph when you do that. So let me show you. So this is, you start with one vertex which has this, and every time here not only one graph comes in, one vertex comes in, it comes in with say two friends, and then it connects with the existing network. So as you can see, this blue thing is slowly starting to become a hub in this. Okay, so in view of time, I'll not go into how this looks like. There is a lot of thing about geometry. So let me go back to the friendship paradox and tell you my few couple of things. So this year we proved this result that all for Erdős-Srény configuration model. I didn't describe you configuration model, preferential attachment model, but generally if a graph converges, then this profile function of the bias also converges. So there is an fx which you can identify explicitly. I'm not giving you the formula. I'll show you how ugly it is, but it is quite explicit. You can calculate that this fnx of the bias converges. And in principle, like if you choose x to be 0, that also converges. So 1 minus fn0 converges to 1 minus f0. Now, what is 1 minus fn0? This means the proportion of vertices which have non-negative bias. So you're looking at the number of vertices which have not only, it has more than 0 bias. So you're looking for that. And that we are saying that it converges to a function which is 1 minus f0. And from there, the friendship paradox also holds. But we say that if 1 minus f0 is greater than half, or f0 is less than half, then we say the friendship paradox is significant. So everybody sees a bias. So almost everybody is positive. So they see bias there. And that is, the friendship paradox becomes significant in that sense. And so here is a formula for the Erdős-Srény random graph. So as I said, in the Erdős-Srény random graph, you choose a P and you fix it. Say suppose P is lambda by n. I didn't say the reason why I'm choosing this, but say suppose it is lambda by n. So then you can write down explicitly the expression for this 1 minus f0. So this is the proportion. So this whole ugly expression is the proportion of vertices in your Erdős-Srény random graph which has positive bias. It's an open conjecture. We could not prove this expression is greater than half. So it looks ugly. We have simulations. As you can see, the simulations clearly suggest that if lambda grows, it is converging to half, and most of the time it is beyond half. So and if lambda is very small, then it is almost close to 1. This we can prove. But intermediate regime, that this is always bigger than half, this we cannot prove. And we know the profile function, how it looks like. So I'm giving you just an asymptotic how it looks like. It's a sort of an exponential. It has like a exponential tail and other things. Okay. So Bikram, I'm over time, but can I take just 30 seconds to wrap up?
Yeah, no problem.
Okay, so let me just take 30 seconds. So as I was saying, that this result is more generally true about, so you need very minimal assumptions on your graph uh, to make this result true. What we could not prove, which was very dissatisfying, whether the Erdos-Sweeney random graph is significant. There is an open conjecture. Just I warn you that this open conjecture is so tempting. We have said it to many people and they have lost sleep for a few days. And but you are most welcome to look at it in our paper. And so this is now appearing in a journal called Probability Theory Related Fields, and it's an open conjecture there. So if you are interested. Now, the thing which we are also interested was, so degree is one way to measure sort of centrality, so number of friends. Google PageRank is another one, like which kind of, I don't know, many of you might have known, but when you search something in Google, then essentially what Google does is it produces the top one, which is the most significant for your search. And there is a way in which it orders the web pages. So essentially what it's doing is, in the World Wide Web is a big graph, and it is putting ranks according to the words which you are searching for. So this is a way of putting centrality measures. Now, okay, we have a proof now that the centrality paradox for the Google PageRank is true, but we don't have any results for random graphs and as such. So this is also kind of open, but what about other measures? Just one point about this general proof. This all depends. So all the expressions you saw come from what is called trees. So this is a counting problem on trees, which possibly you have already heard in Manjunath Krishnapu's talk before. So I'm not going into that relation, but if you read the paper, there are more relations with the trees there. Okay, so thank you for listening and feel free to ask any questions.
So, does anyone have any question? Maybe we can wait 1 or 2 more minutes if anyone has any question.
Yep. Good, Tejas.
Uh, Sir, can you go back to the graph and the simulation that you did for the function graph 1 minus
Yeah, this is the,
is f0 less than half? Okay.
yes. So I've not written it in terms of probabilities, but this has a expression in terms of the, so if you know about Poisson process, so Poisson random variable, this can be written in terms of a Poisson random variable. So this is a probability of certain event happening. So that's the thing. I have just written it down explicitly because it has exponential and other things just to look at, but you can this in our paper also you can see that it's written in terms of probability of a certain thing happening. There was a question, I missed it somewhere. Where can I see it?
Oh, he's saying actually it's hard to get comfortable with the terminology.
Yeah, okay. No problem. Now you
And
see once, twice, and this will be now uploaded to YouTube also perhaps. So maybe it takes time to understand these things. Yes. Just send me an email. Feel free to send me an email. I'll send the slides. just it's quite, the slides are quite big, so I'll try to convert it to something which is more sendable, because it has the videos as you see. So just send me an email. I'll send you the file. No problem about this.
Yeah, I will then send you.
Okay. Google search, PageRank algorithm works pretty well now. So I think they will give you my right email address.
I think there are no more questions. Uh, Thank you, sir, for such a wonderful talk. Thank you, everyone, for participating.
Yeah, good. Okay, bye bye. Thank you.
Thank you. Thank you, sir.
All the best.